In this video, we are going to continue looking at sort of advanced aspects of Lewis dot structures, specifically when the Lewis dot structure actually doesn't have all atoms with a full octet, but the atom itself, the molecule itself, is stable, does still exist in nature. So there's three subcategories of these exceptions to the octet rule. And the first one is an incomplete octet. And this is a situation where no matter how you rearrange the electrons into double bonds or triple bonds, there just aren't enough electrons to give every atom a full octet. And this happens when you have an odd number of valence electrons. So an example of this is nitrogen dioxide. So not nitrite that we looked at in the previous video, but this one doesn't have the extra negative charge of the extra electron. So it only has a total of 5 plus 12 or 17 valence electrons to use. Because that's an odd number, we're never going to be able to make every atom have a full octet. But this molecule does exist. Because it has an odd number of valence electrons, though, that is a clue that it is quite reactive. So nitrogen is the central atom, and of course we draw 2 bonds or use 4 electrons to connect to the 2 oxygen. Now we have 13 electrons left over, and we can use 12 of those to fill the octet of the outside oxygen. I have 1 left over, and I'm going to put that on the central atom. So now if I look at nitrogen in the middle, it actually only has 5 electrons around it. It needs 8 in order to be perfectly stable. I'm out of electrons. And when we're in this situation where we're out of electrons, this is exactly when we use double or triple bonds. So I can't, if I make 1 double bond, right? If I were to make 1 double bond like this, I could bring the number of valence electrons around nitrogen up to 7. If I were to make another double bond, let's say with the other oxygen on the left-hand side, what that would do was actually be more than an octet. And nitrogen can never have more than an octet. So this is as far as we can get. The other thing that we need to notice is that this is actually another example of resonance, what we just looked at in the previous video, because I happened to make the double bond with the oxygen on the right, but we know there's nothing that says that I couldn't have made the double bond with the oxygen on the left. So both of those 2 structures are possible. And what is the reality of it is that it's neither one of those 2 structures actually occurs. It is more like each of those bonds is 1.5 bonds. And so this molecule, that central nitrogen, never actually has that full octet. It gets pretty close, but not all the way. It gets up to 7. The thing is that it's still stable. And so you just need to recognize that sometimes that happens. Not all the time, but sometimes. The second one is sub-octet. Sounds like it's the same thing, but it's a little different. Sub still means under, but it happens with 2 very specific elements, beryllium and boron. If you look at a periodic table, beryllium is the element that's here, and boron is the element that's right there. So they're both at the very top of their columns, which means they're very small. Beryllium is a metal, and boron is a metalloid. So beryllium should never even make covalent bonds, but one of the things that we have sort of oversimplified throughout the course so far is that bonds are either ionic or they're covalent. And in reality, there's an area in between where they are more covalent than ionic or more ionic than covalent. And beryllium is a good example of that, that beryllium's bonds, it will often bond with fluorine or hydrogen, another really small atom. It will make what we consider covalent bonds, even though it's a metal. And that's really because it's so small. Beryllium will make 2 covalent bonds, and it will be stable. And that's that. It's only beryllium can do this. This is the one element that can do this. It will be stable with just 2 bonds, right? It seems like this is not the octet rule, right? But we know that this molecule exists. Boron will do the same thing, but when boron does it, usually does it with 3 bonds. So boron and beryllium, because they're so small, they can actually form covalent bonds, and the central atom has less than an octet, but it's still really stable. So you just need to remember that it's beryllium and boron are the 2 atoms that could do this. This leads to another sort of subset of covalent bonds, which is called a coordinate covalent bond. I just want to make sure that you have heard this term, because it does become really important in advanced chemistry classes, but this is all we're going to talk about it here. A coordinate covalent bond is when one atom donates both electrons. So this is called, again, this is not, you need to know the definition of a coordinate covalent bond for the test, but there's a lot more applications of this. This is a big way that Lewis acids and Lewis bases bond and behave. That's a category of bases and acids that we won't even talk about this year. But we may remember that NH3 is ammonia, and ammonia has a lone pair of electrons on its central atom. And so what will happen if I take ammonia and I mix it with a boron, we would call this boron trifluoride, it will make it so that we will actually get a molecule with boron actually covalently bonding with the nitrogen and making a larger molecule. And if you think, where did the electrons come from that bond? They're these electrons, right? One atom donated both electrons for the bond. That gives boron a full octet. Remember, boron is, an example of this incomplete octet. It can be pretty stable with just 3 bonds, but it could also be stable with 4. And our final exception to the octet rule is when we have an expanded octet. An expanded octet, it means exactly what you think it means. It means that you can have more than 8 valence electrons. So it's either 10 or 12 valence electrons. And this can be stable. Remember, that would be 5 bonds or 6 bonds or some combination of lone pairs and bonds. This only happens with elements where the central atom, so we're looking at just the central atom here, the central atom has electrons in the 3rd energy level or greater. So basically we are talking about phosphorus and beyond. So this is one of the places in chemistry where we're actually not exactly sure how this works. The leading theory, remember, a theory is just an explanation of an observation. So the leading theory as to why some molecules can have an expanded octet, why some central atoms can have more than 8 valence electrons, is that they have to be in the 3rd energy level or greater. We know that the central atom has to have electrons in the 3rd energy level or greater. And we have theorized that that means that it's somehow taking advantage of those d orbitals. Something like phosphorus doesn't have any electrons in the d orbitals, but we know it has electrons in the 3rd energy level, and the 3rd energy level can have d orbitals. So that's our theory as to how that works. There has been some within the past 5-6 years, some experiments that have led us to move away from that theory. But at the end of the day, we still are not really sure how this works, but we are 100% sure that these molecules do exist. So an example of this is Xenon Tetrafluoride. And the first thing you may notice is, hey, wait a second, we said noble gases can't really bond. Well, they don't bond in nature, but this is a molecule that we can make in a laboratory. When we draw its Lewis dot structure, it's exactly the same as we would always draw a Lewis dot structure. Xenon has 8 valence electrons. Each fluorine has 7. So 8 plus 4 times 7 is going to be 28, 36, right? So this will have a total of 36 valence electrons. The xenon will go in the middle. So the xenon goes in the middle here, and the 4 fluorine come off of it, just like always. So the rules, or how we draw Lewis dot structures, doesn't change when we do any of these different exceptions to the octet rule. I've used 8 electrons, which means that I have 28 left over. So 28 left over. I put 6 around all of the outside fluorine. That's going to take up 24, which gives me 4 left over. Remember, when we're drawing Lewis dot structures, we must use all the electrons. Those 4, we just put sort of opposite each other, still in pairs, because we know electrons exist in orbitals as pairs of electrons, and we just put them around the central atom. This will have some implication when we look a little further into the shapes of these. Okay, there's 2 more of these. This is a great chance for you to pause the video, take a look at, do out these Lewis dot structures. Remember, any leftover electrons, they just go on the central atom. So the first one we're going to look at is chlorine trifluoride. Again, we said halogens are rarely in the middle. Well, here's an example where they are. So total number of valence electrons, 7 plus 21 equals 28 electrons. Chlorine's in the middle with 3 fluorine coming off of it. I use 6 electrons. That gives me 22 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That gives me 4 left over, and I just plop those right on the central atom. SF6, sulfur is 6, fluorine is 7 valence electrons, and there's 6 of them. So that would be 42 plus 6, or 48 valence electrons. Sulfur is going to be in the middle. Where do we put these fluorine? Well, we usually put 1 on top and 1 on bottom, and then 2 kind of coming diagonally each way coming off of it. Right? So I've made my molecule. I have to subtract the 12 valence electrons that I've just used, and that gives me 36 left over, and this is actually a perfect number. That will give me enough electrons to put 6 around each of the outside non-central fluorine atoms. Right? So I've used up all my valence electrons, but you can see in both of these scenarios, sulfur and chlorine actually have greater than 8 valence electrons around it. Chlorine on the left has 5 pairs or 10 electrons, and sulfur has 6 pairs or 12 electrons. But these molecules do exist. They are quite stable. So they're just exceptions to the octet rule that actually turn out to be pretty stable.